So we have 3 of these defocusing disks on the interior of the boundary, making this like bowling ball shape. And we want to understand the dynamics within that. Okay. So what we know is that as two trajectories flow along, they bounce off. And because of that curvature, they're bouncing off sort of in different directions. And they start having wildly different behavior very quickly between these two. And so we get this sort of mixing behavior throughout the system where we start seeing the trajectories, which are initially very close, sort of start to spread out. So we very easily could see that like we can totally evolve this, and we can evolve the stability, and we have a natural Poincare section given by the boundary on the outside as well as the boundary on these defocusing disks. But once again, if you see a symmetry, you must use it. And we can see that there's another symmetry about this problem, which is the idea that if I pick, say this is the center of my disk, I have a 3-fold symmetry going on in each of these disks. So in fact, I can do an identification where instead of, and I know it doesn't look necessarily even, but that's mostly because my drawing is not incredible. The idea is that instead of considering the whole of this boundary, we can actually consider a subsection, which is just given by these coordinates right here. And so we end up getting a symmetry reduction in our system to a much simpler, hopefully, and smaller space, which holds out redundancies. So for instance, in the original system, let me erase this and go back. In the original system, we would see this trajectory, and this trajectory, and this trajectory as 3 distinct trajectories. But of course, when we're trying to build some sort of physical observable where we are not given the coordinate system to begin with, right? We want to make sure that we treat all of these on the same ground. And we want to remove some of this sort of seemingly arbitrary distinctions between these points. Whereas in the new frame, in the reduced frame, these all correspond to a single reduced orbit, that being this one right here. Okay, so this is some of the power that we get from discrete symmetry reduction that allows us to sort of take possibly very complicated physical situations. Like we're going to see how using these symmetry reductions, we can get a better understanding of sort of the inherently chaotic dynamics of the system, as opposed to things which can be quotiented out. Okay. And just sort of to pull it all together, I do want to comment that in some sense, you know, this billiard is a Hamiltonian flow and can be formulated in the exact same language that this can, right? It can be formulated exactly in those equations, but because you have these boundaries, there are some additional technical things that you need to add in to your Hamiltonian function, your energy function. Just be aware that there are ways that you can formulate this sort of direct evolution followed by this reflection right here as being Hamiltonian system on the same framework as the simple harmonic oscillator.